Well, it is my privilege to introduce our keynote speaker today, Mr. Tom Siebel. Many of you know of Tom. He's a great friend of our school and of CITRIS. But I will tell you a few things. From the mid-80s to 1990, he was an executive at Oracle Corporation, where he held a number of key positions. Later, he was the founder, chairman, and chief executive officer of Siebel Systems, which was acquired by Oracle in 2006. He's currently the chairman and CEO of C3 Energy, which recently changed its direction to C3 IoT. Tom has many accolades and many distinctions. I will just mention a brief sampling. He was elected as a member of the prestigious American Academy of Arts and Sciences in 2013. He has been very generous with his time and energy. He has been on the board of advisors at the Stanford University College of Engineering, at the University of Illinois College of Engineering, and of course at our College of Engineering here at UC Berkeley. He was also been a trustee at Princeton University, and he's the founder and chairman of the Siebel Scholars Foundation and chairman of the Siebel Foundation. Among his other accolades, he has been recognized as a business leader and entrepreneur. Just a few, he was recognized as one of the top 25 managers in global business by Businessweek from 1999 to 2001. He was the CEO of the Year by Industry Week in 2002, and he was recognized as the Master Entrepreneur of the Year by Ernst & Young in 2003. Tom is an extremely generous and energetic philanthropist. He has ranked number 5 and number 3 of the world's top 25 philanthropists by Barron's Magazine in 2009 and 2011. In 2007-2008, he was named as one of the top 50 most generous philanthropists by Businessweek. The Siebel Foundation, that was founded in 1996, is active in support of the homeless and underprivileged, educational and research programs. One of the iconic programs that they have worked on very successfully was the methamphetamine abuse prevention program, and of course on alternative and energy solutions. The Siebel Foundation most recently created the Siebel Energy Institute that includes now nine of the world's top universities, and it's headquartered at Berkeley. I have the honor of being the local director, and Sakar Sastry, as dean, is the global director of that institute. So with that, I would like to invite Tom to come to the stage. Thank you, Tom.
How are we doing? Good afternoon, everybody. My name is Tom Siebel, and it's a great honor to have the opportunity to talk with you. And I'm going to talk about, this is my 4th decade in the information technology business, and we've been spending the last, well, is this going to work? Maybe not. Old school. We have spent the last 7 years and a couple $100 million, building a platform that we focus primarily on building IoT applications for energy value chains. And so if we look at the energy value chain, it is, as it exists as of the beginning of this decade, and it's called the grid. And the grid has been identified as the National Academy of Engineers as the most significant scientific achievement of the 20th century. And it is pretty much, as of the beginning of this century, it is in every embodiment pretty much as drawn up by Thomas Edison and George Westinghouse. At one end, we boil water. You use that to spin a turbine, rotate a magnet, generate a current, step up the current to high voltage, transmit over long distances at high voltage, medium distances at distribute it over medium distances at medium voltage, low voltage to a meter, and then on to a consumer. So this is the value chain that we've been focused on. And underneath this value chain, and this pretty much runs the same in China, in France, in San Francisco, and in all of the industrialized world. And now in response to, and for some reason, all of these businesses, curiously enough, tend to run, all of these grid operators tend to run these operations as separate businesses that don't communicate with each other very well. And in response to the needs of these businesses, the information technology community has developed, think this will work? Thanks. You know, kind of classic second-generation enterprise software to solve the problems of the various segments, be it customer care and billing from SAP, CRM from Siebel Systems, meter data management from Itron, work order management, voltage control, outage management, inventory management, SCADA systems, and what have you. And like all of these, and these tend to be built on top of relational database technology, and for a lot of reasons that we don't need to get into today, these information systems tend to not want to share information. It's very difficult to share data across these systems. Now, this value chain is going through an upgrade this decade, where all these devices are, as all value chains are, which gets us into another IoT discussion. But this utilities have to be one of the leading value chains in terms of upgrading the devices so that they're all becoming very rapidly remotely machine addressable. And we tend to focus on the smart meter, but it's not simply the smart meter. It's the home thermostat. It's the variable speed fan at Walmart. It's the step-up transformer, step-down transformers, reclosers, capacitance banks, vibration sensors on nuclear reactors, pressure sensors on coal-fired power plants, all the PMUs, okay, single phasers on transmission and distribution lines. It is all being censored. And the amount that is being invested to upgrade this infrastructure this decade, to censor this infrastructure, is $2 trillion. And now that may not sound like a lot of money, okay, but that's a lot of money, okay. And so what we have is the interesting, so this begins to look like a fully connected sensor network. And so what we have is interesting collision. We all know about Moore's law and how, you know, and how that has impacted these types of information systems over the last 3 decades. And now some of you remember Bob Metcalfe from Xerox PARC invented this thing called Ethernet. Turned out to be pretty useful, and came up and coined this idea of Metcalfe's law, where he says the power of the network is a function of the square of the number of devices on that network. And so this begins to look like a fully connected sensor network. And so the collision we have here is Moore's law impacting with Metcalfe's law, and it presents some opportunities. So this is a classic case of a cyber-physical system, or basically an IoT problem. And it turns out the utility industry happens to be one of the leading industries in terms of censoring the value chain. And so what we've been working on for the last 8 years is developing a platform that, step back once. Another secondary effect of this censoring that's obvious is the amount of data increases. And it increases by actually about 8 orders of magnitude. So if we read this meter once a month, that would be 12 times a year. If we read it like we do in most of the world, okay, probably about half of the US today, most of Europe, and all of our homes when we grew up. Well, if we have a smart meter, we read that every 15 minutes. That would be 32,000 times a year, or 4 orders of magnitude. When we look at these PMUs, phasor measurement units, which are giving power quality signals on transmission and distribution lines, these guys are sending out signals at, you know, like 60 hertz cycles. So now, you know, fast math, we're at like 8 or 9 orders of magnitude. So the amount of data becomes staggering. And so what we have been, the project that we've been working on is basically developing a technology foundation that allows a grid operator to take the union of these data, okay, and the data from the sensor network, and aggregate these data into a unified federated image. Aggregate the data into a unified federated image, and these images can get pretty big, okay? And so we have enterprise data that they told you about, sensor data for, say, tens of millions of meters or PMUs or whatever they may be, extraprise data coming from social networks, Google Terrain, real-time weather feeds, what have you. And for those of you who have thought about this problem in the last 2 or 3 decades, this is no mean feat, aggregating these disparate data sources into a unified image. So we wanted to build a technology foundation. We have built a technology foundation that allows a grid operator to aggregate these data. Okay, we load these data into the cloud at the rate of about 6 billion rows an hour. Okay, and then adjacent to that, we built an analytics engine that provides persistence, relational persistence for data for which relational databases are well suited, which is still a large class of data, and then key value stores for telemetry. Okay, and then platform services like security and encryption, batch processing services like MapReduce, stream processing, iterative processing, recursive processing, analytics services, machine learning. And in so doing, we can look across the entire value chain in real time. And then we manifest these applications. Okay, we manifest the insights that we're able to realize out of all these correlations and machine learning techniques, exercises, regimens, into a family of applications that basically allow us to apply the sciences of big data, analytics, machine learning, and elastic cloud scale computing, okay, to the problem of power generation, distribution, and consumption in a manner that dramatically decreases the cost, okay, increases the reliability, increases the safety, increases the resilience, and reduces the environmental impact of that value chain. So that's the game that we've been playing. Okay, and you know, what are useful applications? For example, if you have a sensor infrastructure, let's say we look at State Grid in China, where they have 350 million smart meters installed. Okay, at any point in time, 1/3 of those meters are giving them bad signals. You need to sort those out, correct those signals, do firmware upgrades. So AMI, sensor network health. Revenue protection. This is actually of significant economic benefit. In Chicago, $200 million worth of energy is stolen every year. In southern Italy, it's a much bigger number. In Brazil, it's incalculable. Okay, and so it's basically theft detection. Predictive maintenance. This is of some, this is looking at devices and using machine learning to tell the grid operator what device is going to fail before it fails. We'll talk about that a little bit more. Predictive maintenance for generation, grid investment planning, demand-side management, grid cybersecurity, okay, customer engagement for residences, commercials, and enterprises. And this is what we're doing. And so we've been installing these systems today, large-scale cyber-physical systems, at about 20 instances around the world. I'll talk about one. This is ENEL. ENEL is a utility based in Rome. They have 61 million meters in 40 countries. Putting that into perspective, there are 100 million meters in the US. So this is reasonably substantial. This is roughly a 90 billion euro organization. In Spain and Italy, they have 32 million meters in Italy, 12 million meters in Spain. Okay, and here what we did was we aggregated the data from their SAP billing system, their metadata management system, their advanced meter infrastructure system, their work order management system, their producer system, their outage system, grid network connectivity, enterprise energy management, their installation vendor system, 2 different flavors of SCADA systems, Google APIs into terrain, okay, and social media, and then historical and real-time weather. This is 7 trillion rows of data aggregated into a 750 terabyte data image that grows at the rate of 300 gigabytes a day. Okay, and then we process these data, okay, in ways that, and we persist these data in the cloud, okay, and then apply stream, batch, and analytic services, and ultimately machine learning. And the specific applications that we deploy at ENEL include revenue protection for Spain and Italy. This is basically looking at the telemetry alone to tell them who's stealing energy, how much are they stealing, and how are they doing it. Secondly is predictive maintenance. This is a pretty interesting application. So when you think about if we're dealing with 40 million meters, okay, we're dealing with hundreds of millions of different assets in the grid infrastructure. Power poles, power lines, transformers, single phasers, substations, reclosers, capacitance banks. Okay, and the way that the grid works, you know the way that works in San Francisco is it works until the lights go out. Okay, and then they send out people with trucks and voltmeters to climb power poles and go down manholes and test devices until they find boxes that aren't conducting electricity, and you keep replacing boxes until the lights go on. That's basically the state of the art as of 2015, 16, believe it or not. Well, we can, by looking at all the telemetry with very high levels of precision, okay, we can tell them we can tell them what devices are going to fail next. What's the probability of failure? Why is it going to fail? And what's the time frame in which it's going to fail? Well, the implications for safety are obvious, and cost are obvious. If you fix it on a scheduled truck roll rather than 2 in the morning in the middle of a hurricane, the cost implications are pretty obvious. Actually, the economic implications of this application, revenue protection, for a US or European grid operator is about $10 per meter per year. Well, if you have 60 million meters, this is significantly non-zero. Predictive maintenance, the economic and social benefit of that is $20 per meter per year. The other two applications that we're doing are predictive maintenance for 65 gigawatts of conventional generation facilities. Conventional generation, this is a coal-fired power plant. Okay, basically there's two types of assets you need to deal with there: coal pulverizers and water pumps. I mean, all you do is you boil water and move it around, right? Okay, and we can actually predict precision. Our precision on predicting failure in water pumps is greater than 90%. And then we're doing 10 gigawatts of renewable generation. These would be wind turbines, and then CRM. The economic benefit of this application to ENEL is 291 million euros a year in recurring economic benefit, and this is the largest production IoT application in production on the planet Earth. Okay, so in any vertical. So the economic benefit of this entire stack of products that we built, that we would provide to ENEL, is order of 7 billion euros a year in recurring economic benefits. So this is pretty significant. Okay, when you're in the boardroom talking about 7 billion euros a year in recurring economic benefit, and the people in the boardroom believe that number to be true, there's a basis for an interesting conversation. Now, we have deployed these applications at large scale at 20 installations around the world. Department of State for 20,000 facilities. ENGIE is roughly a 90 billion euro integrated energy company based in Paris. You used to know it as GDF Suez, ENEL, PG&E, Exelon, and what have you. Now, this is a unique case of a IoT application that would be applied to energy markets. And we spent the first years focused on energy markets. But if you look at what's kind of going on with IoT, okay, this is basically all value chains are being censored. Whether it's automotive, whether it's healthcare, home. I mean, how many sensors will each of us be wearing or have embedded, someplace in our bodies in the next 10 years? It'll be order of a dozen, right? Okay. But this is the rate at which this IoT phenomenon is taking place. Okay, and there is a school of thought, and if you're interested, or if you refer you to this article, it's in the November 2014 issue of Harvard Business Review by a guy named Michael Porter, who is a pretty famous professor from Harvard who wrote all the books on competitive strategy. And he argues that this next generation of computing is all about smart connected devices. And if companies don't have platforms to address this opportunity, that they will not be able to be competitive. So this is the expected growth rate. okay, in the software business as it relates to these IoT applications. And what we're looking at is an entire replacement stack for the enterprise entire replacement market for the enterprise application software stack. Now, this is not the first time since the 70s since we've seen entire replacement markets. When we went from mainframe computing to mini computing to personal computing to internet computing, when we went from VSAM systems and ISAM systems to relational database systems, when we went to enterprise software, when we went to the internet, when we went to mobile computing, those were all entire replacement markets. And this is another one. So McKinsey sees this as the amount of value here in that'll be companies will accrue to their customers from IoT in health and fitness, home automation, retail automation, office security, factory operations, worksite vehicles. This is $5 to $11 trillion a year in recurring economic benefit. Well, 10 trillion is roughly the size of the Chinese market. So this is bigger than a bread box. And so this is what we've done. This is a platform as a service that it runs on top of cloud providers who provide infrastructure as a service underneath it. And you can think of it as three kind of chunks of functionality. One is the data aggregation capability, and the secondly is the data processing capability. Now, this is not that simple, but we solved it. And the idea of processing petabyte data sets, 15 years ago was almost unthinkable. The idea with this over here, which is about visualizing the data, there's a lot of people focus on this, but this is trivial. Anybody with a couple of tattoos and 1 week, say a month on the internet in a training class can do this. This stuff is actually kind of hard. Okay. Now, once this goes away and you can aggregate the data and you can process data sets that large, okay, it's like a video game where you get to the 11th level. It basically becomes a machine learning problem. Okay, and that is just wide open territory in a field that I know that some of you know something about. It appears to me to be embryonic in its state. I think the cell is divided about 4 times. Okay, now when we realize the potential of this, we realize the potential of IoT. So now, as we move from C3 Energy to deliver to these products, what C3 IoT is doing is providing a platform to all of these markets: healthcare, transportation, oil and gas, aerospace, financial services, to help companies, realize this future. And this is the largest one we're working on. I don't know if we'll really do it. They want to do it, but it's hard to do business in China without getting ripped off. And I'm getting a little old for this, and I'm not really know if I'm up for it. Okay, but this will require, the Chinese grid is larger than the sum of the rest of the world combined. Okay, and they are far, far ahead of the rest of the world, okay, in smart energy technology. Nobody's even close. And by the way, I put U.S. in about last place. Okay, Japan is ahead of U.S., Europe is way ahead of the U.S., and China is far ahead of everybody else. They've deployed 350 million smart meters so far. They'll have 600 million installed within 5 years. In order to deploy what they're calling the Internet of Energy, which is a mandate of the 13th five-year plan, which is basically exactly what I showed you, and a name that I thought I coined, but I guess I didn't, because they own it now. This will require aggregating 200 petabytes of data. We'll run this in 50 data centers on 200,000 virtual machines, and it will be the largest production deployment of any kind ever deployed on the planet. So that's the scale of what we're doing. The trouble is, how do you do it without there's this issue of like massive taxation and intellectual property theft without expressing any moral quandary. It's just kind of no fun. One comment on information technology: there's kind of one alternative to this stack, and they all have the same name. This is a model-driven architecture. Okay, so do a Wikipedia on that. Okay, it involves kind of domain-specific languages, and every other alternative that's in the market today is using a technology that was developed in the 60s that you know of as structured programming. Okay, and what people are trying to do is take about 70 or 80 independently developed programs, source code stacks that happen to be open source, which is fine, and use structured programming to couple them together into an integrated stack that works. This would be every other solution that's in the market. I would argue that that's a pretty difficult problem. So anyhow, that's what we've been about. We've been about taking this step function of technology that became available at the first decade of this century, cloud scale computing, big data, machine learning, social human-computer interaction, and applying it to initially to the value chain of energy production and delivery, electricity production delivery, now oil and gas, and other value chains. And it's been a fascinating experience. Questions?
So we have time for maybe one or two questions. Thoughts?
Thank you. I'm curious about the division between applications and platforms. When you talk about machine learning, you talk about machines that achieve certain values, and the formulation of those values is very complex, right? Especially in energy, are these business values or civic values or values of fairness of access to power? So how can you connect the formation of value to, in terms of human interests, to machine learning more precisely?
The formation of value as it relates to human interest to machine learning.
Yeah,
okay, if I understand the question, okay, I think it's in the human interest that the lights don't go out.
Right.
Okay, do I understand that? Would be something that's in the human interest?
Sure.
Okay, well then we can use the telemetry, okay, to identify transformers, substations, single phasers, and reclosers before they fail, replace them before they fail, and then the lights don't go out. So no, we have to design a machine learning classifier that'll do that.
So then who pays for it? And who pays how much for it? And which neighborhood do the lights go out in first, if there is a problem?
Well, in the United States, okay, in China it's very simple. They just do a mandate and everything happens, right? Yeah. Okay. In the United States, it is probably the worst case scenario. You have 100 million meters serviced by 3,250 utilities, which means the average utility has order of 30,000 meters, regulated by hundreds of overlapping regulators. And these regulators can't do anything without the permission of their regulator. But ultimately, to put these systems in requires the approval of the regulator, and it works, and then it gets worked into the rate base. So ultimately, the ratepayers pay for it. But let's think about this. If we put volt-var in, and we can bring voltage and reactive voltage into phase, this results in 8% less coal that we're burning. So it costs something to put it in, but the economic benefit is like $40 per meter per year. And so the ratepayers pay for it, but the benefits of the whole stack are like $300 per meter per year. So they by far exceed the cost.
Thank you. Maybe one more question?
You sort of touched on, the progression of platforms and the design methodologies that go on them. Things have changed for design and software engineering for mainframes was different from internet-based fluid social networking, say. Do you see any sort of general way of distinguishing between architecting, designing, and implementing for cyber-physical systems versus your garden variety social network, even for that?
Yes, the complexity of these things.
And how do you teach people to do it?
Okay, I think this requires everybody who's trying to solve this, who's in the market today, is trying to use structured programming to solve it. Now, if you use structured programming, the order of complexity that a programming team needs to be able to comprehend okay, is order of the number of unique sensors, actually the number of unique fields of data from the sensors, times the number of unique enterprise data sources, actually fields, okay, times enterprise sources, times programs that you're trying to cobble together, times the number of APIs, times the number of machine learning algorithms, times the number of user interface expressions. Okay, and if you work it out, it's like order of 10 to the 13th. Okay, it's not a programming team can't grok it, and so the next generation would be what we call these model-driven architectures. We're using domain-specific language or type systems, and so we've abstracted all that complexity for the programmer, so they don't need to deal with it. They just deal with types. And types then will have, these are domain-specific languages, okay, that will tend to have attributes and, actions that we can, and methods. And so we're dealing with, say, order of 1,000 things, okay, that a programmer or programming team can then manipulate, which makes the problem tractable. But this is why you find problems, like there are companies out there who remain unnamed, okay, they're like some of the largest, electronic appliance manufacturers in the world, okay, who has spent, $4 billion in the last 3 years trying to cobble something like this together with 3,000 programmers and don't have one system in production in the world, trying to use 1960s technologies. And so I believe that it requires a new way of thinking about programming, a more modern way of thinking about programming to solve the problem.
Great, thank you.
Thank you very much.